we're going to look at zero order kinetics. Zero order kinetics are actually even simpler because the rate of change in A, the rate of disappearance of A is constant. It doesn't depend on the concentration. What are the physical situations that would happen? Anytime when the reaction is dependent on the available surface area for reaction. So for example, the turnover or decomposition of some molecule on a catalytic converter, because that'll just depend on how many catalytic sites are available for your gas to visit. Sublimation from a solid where it's just sort of dependent on the surface area, which doesn't change. Enzyme catalysis where not the products, or the reactants are in surplus, because they're all just sitting around waiting for the enzyme to free up, right? The enzyme has to bind each of the reactants to produce it. So if the reactants are in surplus, then it's just going to be a constant rate, the rate at which the enzyme can turn over reactants. So zeroth order kinetics are actually relatively common. Okay, so the integrated rate formula is just this. And this is pretty straightforward. This one we could actually plug in pretty easily to check that it satisfies the calculus, right? Because we take the derivative of A with respect to T. I'll assume you guys have seen some calculus equals d dt minus kt plus a0. All right, so the derivative of something times a constant is just the constant, so minus k. And then the derivative of a constant is 0. So we get d a dt equals minus k, which we can rewrite is now just using a differential. Or it could be either finite or not, k. So we can plug in and show that this equation indeed satisfies this differential equation everywhere. Okay, so this is, of course, very nicely in the form y equals mx plus b, where t is our independent equation, right? Y equals mx, where the slope is minus k, and the intercept is simply the initial concentration. These are very easy to read off. Half-life, let's plug in and solve for the half-life. So A0, again, the half-life is where the concentration is at the initial point, equals minus k t plus t1 half-life plus a0. Subtract a0 from both sides, minus a0 over 2, so to minus k t1 half. And so we're solving for the half-life t1 half, divide both sides by k. T1 half is equal to a0 over 2k. That's what we got over there. So the half-life, again, is dependent on the initial concentration. So we can use the same, plugging into any of the integrated rate laws is essentially the same process. You've got a formula, you take the data, you plug it into the formula. We have formulas for the half-life, but as you can see, they're all relatively easy to derive as well. So those are the examples of the integrated rate laws we can see. We're sticking with unimolecular rate laws, but if you take a class in chemical kinetics, you'll deal with rate laws where you've got changes in multiple reactants.